It's a pleasure to be here with you all today. I wanted to talk to you about what does it take for robots to really be ready for our world. How many of you have seen a ton of the humanoid videos? Maybe the G1s, like, you know, doing some cool things, the backflips, the running. When you think of maybe some of these humanoid hands, what kind of comes to mind at the moment? Any videos in particular?
They're kind of gingerly.
Yeah, big, clumpy hands, and they have trouble doing a lot of manipulation. And if you actually go to like ICRA or IROS, the number one thing to kind of like showcase them is actually have these things doing boxing. And I think it's not because they want their robots to be violent, it's just that's what the hands are good for right now because they struggle to actually pick things up. So when we think about what we actually want robots to do, I think this is a very important place to start the discussion. Before I jump further, I want to just first give a shout out to a lot of the amazing researchers in my lab, and I'll be able to showcase some of their work. But our lab does very broad things, and I'm only going to be able to show you really a portion of what we do today, but please check out their work later. So if I go to Webster Dictionary and I ask, what is a robot? The general public agrees that this should be a system that's capable of performing complex tasks, and they immediately recognize it involves something like grasping and moving objects. And so when we really think about that vision for robotics, it can go all the way back. I think only a few people in this room can raise their hand and remember watching Jetsons on TV. I'll put my hand down, actually. But in 1962, you had the Jetsons. And so you have to give respect to those graphics. They did it all by hand. And it was 1962. But even then, they recognized the value of having a system, right, that could do the hard tasks. And if you talk to a fundamentalist in robotics and you go, well, what is the purpose and point? We'll raise 3 Ds, the 3 Ds of robotics. We should be able to handle the things that are dull, dirty, and dangerous for people. You think back perhaps to the last pandemic, having robots that could actually work in that space and do things that we may not have wanted to expose human doctors to would have been helpful and could have even saved lives at certain points. So another aspect of this is not only do we expect robots to be able to do what humans are able to do, but we recognize that maybe if a machine is doing this, perhaps those abilities could be superhuman. You could be more accurate, faster, more precise. You don't have to stop. How many of you remember seeing Star Trek Next Generation? They do some reruns. Wow. Okay, yeah. So, all right, I'm over 30. But this is also something still recognizing that superhuman ability. So check this out. So this is Data. He's an android, one of my favorite characters from this show. And he's going to impress this child with something that's very easy for him to do. So here you see this both speed and precision and accuracy and strength all encapsulated. So what industries could stand to benefit from these types of systems that have embodied intelligence and can do this advanced manipulation? I'll raise a few. This is not an exhaustive list, but you could think of perhaps assisted living, helping people age in place longer. You could think about agriculture, the ability to gather crops in harsh conditions, gather and plant, harvest and plant. And even in fulfillment in industrial solutions, having robots that could help with long hours and many packages to deliver. Amazon, for instance, delivers 16 million packages a day. And what you'll see in a moment is they're only really good at doing about 70 to 75% of those with their robots. People have to do that other component, which leaves about 5 million packages daily for people to do, and that number is growing. There have been some early advances in these spaces. So the PR2 co-developed Willow Garage. Steve Cousins, who actually leads the SRC, helped build this. You have an example of this robot working in a domestic space. We have a few agriculture robots we'll talk about more that can do a few basic tasks, but they're really tailored to the specific thing they're trying to pick, and it's not generalizable quite yet. And Amazon making strides to try and have robots do a lot of these complex dexterous tasks and realizing how important it is to be able to handle most of the things that might be in the space the robot needs to address. So let's focus on a few of these and really blow up the problem and take a deeper look. So this is a video from Amazon. They're showing their Vulcan robot. This is the one that was packing things into those shelves. And in fact, one of Mark's previous students actually leads the team that was working on the Vulcan. And if I could take a quick look, remember these numbers: 75%, 60% of these inventories are the things that the robots are able to do. And the one that was picking could only pick up the packages that it could actually use suction on. And we'll see that again. Another example is in the space of manufacturing or assembling phones. So this is a company related to Samsung. Here you see all this very specialized equipment that's been really tailored to try and manipulate these phones to actually assemble them. The challenge is, how many of you have bought a new phone in the last 2 years? Okay, a decent number of you, and they continue to upgrade. If you had enough money, they'd love you to buy a new phone every year, and something has to usually change to make it worth your time, which means you probably need to assemble a new device. And while some of them begin to converge, that convergence doesn't necessarily have to be the case. They can actually change considerably inside if there have been enough innovative advances. So the need here is for robots that can handle both that flexibility and what they're required to do, and if something changes on that factory floor, if something is unexpected, can you adapt? Even in this case today, tons of humans having to do a lot of what should be easiest tasks. The robots can do the soldering and stuff, but when it really comes to that manipulation, which seems basic, we still need a lot of people to do those things. And again, the conditions for those people may not always be the best. In the example for domestic aging in place, over 1.5 million Americans have issues with arthritis. And if you actually look at the list of activities of daily living, this is what's necessary for everyone to kind of take care of themselves. But if you really want to live independently and age in place, you might also need to be able to complete a lot of these tasks as well. So the need here would be reliable systems with enhanced capability and be able to really handle all the tasks that person would need you to do, so that there's not something that's really blocking the rest of their day or their well-being if you can't do it in their home. So if I take again another look at this again, you might see quite a few of these could be accomplished by even one sort of humanoid robot that actually had decent manipulation skills. And I believe there was a showing of Robot and Frank in the SRC maybe a few months ago. And that was really driving it home. There was some adoption challenges, but then, Robot, really stole Frank's heart. So there might be a future there. In the space of agricultural robotics, over 2.6 million workers are actually doing jobs in the case of harvesting and picking. And there's so many factors, as you know, driving that conversation. Having robots that can really assist in these challenging conditions would be really important. And if you think about some of the robotic solutions that exist in this space, a lot of them have been tailored to different aspects. Here was a company that was in Philadelphia. This is a robot that's able to follow the person around, help carry the produce. But these other robots, if you saw, had these very tailored methods of actually interacting with the produce that was in their purview. And so things that matter is, as these farms and farm needs continue to grow, you need to have systems that are reliable, versatile, and they should be able to handle this produce and these related tasks very quickly. And you can see the numbers show we really have to address this soon, right? When you see the size of the farms growing and their expected output continuing to spike, this is something that we really critically need to address soon. So what are the high-level abstractions of manipulation? Some things to consider: when is a grasp a stable grasp? So that means if I grasp it, will I lose my hold on this? Can it fall out of my hand? There's semantic grasping. Do I understand what I'm interacting with? And then there's grasp articulation. How good am I at actually manipulating something in my hand? So let's start with grasp stability. This was really the first frontier, and you actually have in front of you some of the key researchers who laid a lot of the groundwork in this space. Form closure says if I can completely envelop the object that I'm holding, then geometrically this object is trapped. Force closure says when I push against this object, I have a normal force and friction. And if it's isotropic, then I have a nice circular friction cone. And if my fingers are contained in this friction cone, then these can actually reject any external forces that I might experience on this object. And this object is held within my hand, between my fingers. In the space of semantic semantics and grasping, there's been a lot of really cool new tools like vision language action models. Probably a lot of you have heard about them, where you can actually take in both images and words, prompts, and tell the robot what it needs to do in order to accomplish that task. If you kind of blow this up and look under the hood, again, you have this sort of image of the scene coming in, some description of what you'd like to do, and somehow this robot is able to then understand what actions it should take. And so something we're going to talk about later is, well, where did that policy, where did that knowledge actually come from for these systems? You know, spoiler alert, it came from people, but also how well can this generalize to other tasks that you might need this system to do? The other one that needs to be mentioned is the simplistic solution, which is suction. Spoiler alert, suction sucks a little bit, because if the object that you're trying to manipulate is perforated, it has holes, is small, is soft, maybe it's like cloth, the suction might not always be able to adhere. And this can be a lot of items that you might struggle with, and companies like Amazon suffer with these constraints. This is an example of a robot that is even using this sort of suction gripping in the case of like manipulating and sorting these pills. These are small objects, but everything is so well tuned for this system. The suction cup is perfectly the size of this M&M. It's not M&Ms. Don't eat them like M&Ms. For sorting and grabbing these items was really well tailored for that. But again, what if this were soft? What if it were even smaller? You might struggle in those instances. And I'll bring you back to Amazon's Sparrow robot. It's a really impressive thing to see if you ever get a chance in person. It's really cool. This is a video on YouTube showing how these systems can pick everything up, but kind of the secret sauce is all of these have surfaces that are really well conducive to manipulation of this type. I'm also going to take a moment to recognize a really nice taxonomy that Mark Akowski developed quite a few years ago that really took a moment to really analyze all the types of grasps a person with a very articulated hand might use to actually interact with an object. And so you can break this down into, are you just trying to do a power grasp where you're trying to immobilize that object? Maybe for some downstream tool use, but articulation isn't really required. Then precision, which is usually a precursor to articulation, to future actions you might want to take. And so if you begin to study this work, I encourage you to go back and check this out. It's very well cited. You'll see this come up a lot in this space, but this really gives you a good sort of thinking and framework for how those grasps might occur. So what does it mean to grasp successfully? If you're trying to immobilize an object, that means it should be robust to external forces. And then perhaps also you want to be able to reposition it, articulate that object to perform some other high-level task. Another question you might want to ask is, well, are my fingertips compared to the object really rigid? If you think about like two glass or ceramic surfaces touching each other, if there's curvature, their contact area will be very small. And if your contact area is very small, then my question is your friction really high? You're very sensitive to slight changes in motion, which might result in you losing the grasp for that object. So one company that really leaned into this, there are quite a few, and this is actually a full field of study, but soft grippers. And so particularly soft robotics in this image shows how they're actually able to use these sort of soft inflatable fingertips to wrap their fingers around these objects and perform these stable grasps on these objects. So here, precision is not super important. As long as the object can be sort of grasped in this general way, they're kind of trusting the soft, malleable nature of the fingers to surround that object, to immobilize it and allow it to be transformed to a new location. So this is really important. We, implicitly in this discussion so far, all the videos have been, really curated well to kind of show these operations of these different grippers. But what objects are we manipulating? Does this really generalize? Are these robots ready for your home, agriculture, and these other spaces? So I'd like to take a moment and make my own sort of taxonomy of the objects. Here you could think of rigid objects, soft objects, unarticulated, and articulated. So here I have a mug. It doesn't really move. It's a solid object. If you were to push against it, you could probably apply a decent amount of force. And if you wanted to, that would allow you to actually over-constrain the forces needed to manipulate that object. And usually those tasks are translating, picking, placing this object from one location to another. I put this soft plush toy here as another unarticulated object because you can deform it but it really doesn't change shape that much. It'll deform, but when you release it, it'll go back to its original shape. In the articulated object form, you have this example of like a laptop. Its segments are rigid, but it actually can change shape in this sort of quasi-static way. And then on this end of soft and articulated, at the very extreme, we have things like this rope or this shoelace here as well. There was an Amazon picking challenge about 15-ish years ago, if I recall correctly. And they asked a whole bunch of research teams to try and move a lot of these objects between bins. And again, if you look at these at the items here, a lot of them are relatively rigid. And again, I'm being generous with this rigidity. Maybe this soft folder is not quite as rigid. But then even in that selection, there were soft objects as well. And the winning team actually used a suction-based approach, which led to adoption by Amazon. But at the same time, they've inherited the challenges of not being able to really handle all of that inventory, and they're paying for it at 5 million packages a day right now. So many tasks go beyond just grasping, and in-hand manipulation, articulation is required. So let's talk about the levels of articulation you might experience. So here's a very basic example. 1 degree of freedom, screw on a cap. Not very difficult, but this is what you have to do. Maybe sort of like a peg and hole, you have to figure out where that object is, how you interface with it to accomplish this task. Maybe for the sort of manipulation space, you might want to be able to localize an object within your hand. So this is a really cool work called Neural Fields with Neural Fields. And in this work, you're actually able to use multiple cameras to build a 3D reconstruction of this object. And then it's using an optical tactile sensor, we'll get into more later, that's able to actually understand where these fingers are interacting with these objects to begin localizing and actually transforming, articulating these objects within the hand. Similar kind of work by OpenAI. This is the shadow hand. If some of you are in CS, go upstairs, you'll actually see one of these hands. I think actually this hand was donated to us. And the goal here is to actually articulate this object so that you can actually make this cube match a desired configuration. And this system was actually trained in RL, possibly even using Isaac Gym. I have to go back and check. So this all looks cool. Should we all go home? Have the problems been solved? Nope, there are still a few that are out of reach. So what are they? So if as an instructor, if I were to pick a test for these systems and go, this is when you'll pass my exam and you're ready to go into the world, I'd love to see these robots be able to tie and untie very small laces, strings like this. If you could do this, I would bet good money that you'd be able to do most of the tasks we would want you to do in the domestic, agriculture, and industrial settings. And probably as you look at this, you go, yeah, this is a little bit different from what we've been seeing today. This is still pretty hard. So why is this hard? And what would you need to actually overcome these challenges? Well, I think one conversation point that we really need to discuss as a community is, well, what sensing modalities, what perception do you need? Is vision enough? Well, there's this interesting study done in 2005 where they took a participant and they anesthetized their fingers. And as they tried to do this very simple task that they knew how to do for years, light a match, they could show how long it took when the person did it with the sense of touch and with the numbness that was produced in the fingers. And while they were able to eventually complete the task, it took an inordinate amount of time comparatively to do that task. So let's put on our formal kind of robotics hats here and see what components are really needed to overcome this problem. So if any of you have taken Principles of Robotic Autonomy or my class, Collaborative Robotics, or any of these others, we'll really start with this sort of closed loop system, which includes perception, planning, and control. A robot needs to understand what's in the environment, be able to extract a state, understand how that state should evolve, and then understand how it should move itself or interact with the environment to achieve a desired state, and understand how it should adapt to perturbations of the expected state. So what are the necessary capabilities for robotic hands? If I take a hand, what would I like to do? What's my Christmas list? I'd love to have high-resolution tactile sensing, and I'll keep convincing you why this is important. Dexterity, I'd like to have full kinematic range of motion. There should be strength and durability, and it should be relatively human-sized if you want to insert this into human spaces to do human-type things. So how can we improve robotic manipulator perception, planning, and control to complete these more complex dexterous tasks? So the modalities of perception as people, we have our vision, touch, and audio. We also have smell and taste, but we'll assume those are not as useful for this task. Vision, we have great analogs for everything. Cameras are really well evolved. If it's useful, we have microphones, and I'll show you an instance where that is. But touch is still, despite years of work, is still not where human ability is. And what does it take to get there? So just to cover our bases, in the vision space, literally released this past week or so was like SAM 3. If you do anything in computer vision, I've been told it feels like Christmas came early. You have really cool tools like Depth Anything VX, whatever, 3, probably going to be 4 tomorrow, where you can actually track with a single monocular camera what's going on in the scene in an amazing accuracy and speed. And then you have the emergence of these tools like neural radiance fields. Now the hot thing is Gaussian splats and 3D Gaussian splats that allow you to actually represent the world that you're looking at and having a neural network that can actually use vision to reconstruct these scenes with high accuracy, high fidelity, and understanding that 3D underlying nature. For the sense of touch, if we look at what humans are capable of doing, we have 4 different mechanoreceptors in our fingers. They give us knowledge about high frequency touches, low frequency touches, vibration, as well as temperature. And they give us all of this information and they send it back in a sort of physical transduction way. You cause some deformation of the finger, it disturbs these cells, that turns into an electrical signal which your brain then interprets. And if I blow this up, what are we actually sensing? We have position and shape. We're able to determine what we're holding in our finger. Even if those items are very small, we can accurately reconstruct their shape. We have knowledge of temperature. We have knowledge of forces. Again, go back to that sort of knot tying example. To untie that knot, there's occlusion, so you have to feel where those strings are. There are multiple strings, maybe 3 or 4 all together, but you're looking for the string that's actually giving you the most resistance to pull it apart. So you have to have localized sensation of forces, and both the normal friction, planar friction, and torsion are all playing a role when you're doing that sort of sense of touch. And then vibration as well, which there was a really cool study that showed if you actually have a micrometer feature, you may not be able to detect it by just pushing into the surface, but if you can rub your finger along the surface, you can actually detect even those really small events. Audio plays a really important role. I'll focus again really in the context of touch, but there's also broader work as well. Jiajin Wu here in CS has done some really cool work in this space as well. But I'll focus on this work really quickly that is really built on the latest touch sensor coming out of Meta called Digit 360. And they actually used multiple modalities of sensing, tactile image, audio, IMU, and pressure to all inform the system as it performed these different manipulation tasks. And they put effectively a microphone in the system so that it could actually hear those contact events. And in their paper, you'll see they say that their manipulation actually improved with these multimodal sensing capabilities. So next, let's talk about that intelligence. We've talked about the sensing. How do you know what to do with that information? So one option is to use reinforcement learning. In this instance, your robot needs to have access to an environment where it can try and test something, fail or succeed, learn from those failures, successes, which means probably something needs to reset the environment so it can try again and again and again. And then from that, build an internal policy that says, if I'm in a similar state, I believe I should do this action in order to achieve the best possible outcome. Or imitation learning, which requires that I have some sort of demonstrator that first gives me an example of how to correctly perform a task, and then I need to replicate that ability. A condition for this, though, is I'm asserting that that person is conditioning their actions on what they perceive, and they're making decisions, and then they're moving their body in a particular way. And so if you really want to match this model, you need to have similar perception modes or have an effective mapping. And you need to have similar action capabilities as well. I'm not going to get into this today, but I think another really important piece is in all of the imitation learning conversations, we're generally talking about the policy. But if you've kind of had your ear to the ground recently, you'll have heard like a lot of companies are talking about world models now. And that's effectively a system's ability to say, if I take this action, what do I think will happen? And I'll postulate to you that even we as people, as demonstrators, also have world models. But how do you access that? A policy is way easier to access. I can see what you observe if I dawn you with a bunch of sensors, and I can see how you move. That gives me access to your policy, but how do I know what you expect? This is kind of like precognition. If you go to open the door and you don't know the door is open or locked, you're going to move in a particular way. You're going to apply a certain amount of force to open the door under the assumption that the door was unlocked. But then when you feel that force, you then adjusted your behavior based on that force. But there was this whole first initial model you had, which was, I expect the door to be unlocked. How do we give systems knowledge of that precondition, precog or world model that the person had? This is a lot harder, and I think we'll have to think deeper about that in the coming months and years. Moving to actuation and hardware, this is showing for a whole lot of different actuation methods. If you have pneumatics, maybe a person's actual natural muscle, piezoelectricity, a sort of relationship between work density and actuation speed, and these servo motors sit right about here. Additionally, if you actually think about, well, what does it take to build a better motor? Well, one drawback of these, as you make these motors smaller for hands, is you still need that good strength to weight ratio. So either you build a nice transmission system to do some mechanical advantage, or you actually have to be able to have more windings in your coil, inside of your motor. So when you put that electrical signal in, that current in, you can apply more force. But if you actually look at the conductivity of a lot of materials, copper, which is used in these, is right about at the top in terms of the conductivity. Well, I want to say it's about 1.68 times 10 to the negative 8 ohm meter. Check that. We're being recorded. Hopefully that number was correct. I think it's really close. Right above it is silver. And if you go a little bit above that is graphene. But that's about it. There's not a lot of room on that axis to really make systems that are more conductive than that. And that's a challenge to making these stronger and smaller. And if we look at the other end, tendon-driven systems, this is a very popular hand made by my colleague at ETH called the Orca hand. It has all of these motors in the base that are pulling these tendons. Back in the day, we used to use steel tendons. They work great on bridges, great under tension. But under a lot of loading and strength, this other material, Dyneema, works a lot better. So if you've been paying attention on the right side of the screen, you'll see these both going under this sort of tensile test. And that's usually where the conversation goes and stays. But the other challenge here is, well, that's not the only thing that's happening to these tendons, right? These tendons are being wound on your motor. So there's actually a lot of bending stress that's actually happening as well. And so when you actually go and see, why do all of these fail? Why do you really hate your tendon hands so much? Why can't we use simple string, and why don't these really last? This is an issue, right? If you think about those cables on your bridges, no one's winding them up and unwinding them again and again and again. They're just under tension, and that's where they shine. But if you wind them up and unwind them, yeah, you're going to introduce these fractures, and then your system's going to break, and we need to rethink that. So some paths forwards and opportunities. On the perception side, there's some really exciting new tools. So I'll go back to Meta's Aria glasses. So if you want to collect demonstrations from people, they can wear these glasses. They can get first-person views of their scene. Couple this with some of the latest tools, and you have a really cool way to extract, what a person is looking at. You have gaze extraction, as well as understanding the scene and environment that they're in. For tactile perception, there's physical transduction, which I think deserves its own slides, but I only have 50 minutes, so I'm going to focus really on optical tactile sensors. These optical tactile sensors are nice because you're bringing the power of computer vision to touch. So all of these types of sensors here have some similar components. There's some elastomer, gel, fingertip that's going to touch the world. Then there's some internal illumination, some camera that's detecting the deflection of a soft gel, and then a housing that holds everything together. So my lab, the ARM lab, we made our own version of this, but we really came at this from the perspective that we wanted a sensor that was really soft, had a nice contact area, but we also realized the importance of potentially having a really nice grounded truth calibration for our system. I wanted to know the metric position of every position on the surface of this sensor, and if I could, I'd like to have the 4-axis stress field over that sensor as well. So every point on that dome, what's the normal force, what's the 2 planar shears and torsion as a stress field? Because I believed if I had that, that would enable my robot to begin thinking about how it might do things like grab a cord and apply forces and pull things apart. But second, and I'll break this point in a moment, if I wanted to actually collect data from a human and their sensor was drastically different in morphology than mine, if I calibrated it, now we have a common language. We know what we need to sense, we know the position, the forces, and if my human felt these positions and forces, my robot should feel these positions and forces. And I don't have to make the morphology the same if I bother to ground myself in a common metric language. This is our DenseTech sensor. We have two versions right now, the DenseTech 2.0 and Mini. This is showing the explosion of the Mini. This is a pattern that's used to actually track the forces. I'll get into that in a second. We're improving this so that we can stabilize this and make this at scale. Working principle, you have LEDs inside, shines off a surface, back into the camera. All the material in here is translucent. You put some reflective coating just on the boundary so the light reflects back. If there's a lot of light reflecting back, you know that it's pointing towards you. If it's a little bit less, you know that your normal is pointing away. You can then use those surface normal approximations to say, well, if I know what those are and that my surface is continuous and I know that at the boundary I'm glued, I can actually use that to perform Poisson integration and reconstruct my surface. This was done using a lookup table by most other works in this space. We were one of the first to come along and say, let's use a network to actually perform that integration for us. And if you put markers on that surface, particularly ones that have this nice chaotic but continuous pattern, you can track those deformations. And if you really want it to be soft, then aliasing could happen if you have points or squares. But if you have very interesting S-type curves, you can undergo extreme deformation. So one of our early models looked like this. You pass in those two images, feed this through the network, you're able to reconstruct the depth. And then our initial thing could say, if you take some impact on the surface, can you get the net wrench? That's 1 Fx, Fy, Fz, and then 3 moment Mz, My, Mx for the net wrench over that surface. But again, we're not where we want to finally be. This is really cool. This is really great. Really proud of that. But the stress field, I think, is the ultimate goal if you really want to drive that home. To collect that data, because we're so soft, if I push in one area, the other part of the sensor will deform. So our way to deal with that was to actually push into known geometry. So these caps are made out of 3D printed plastic with known geometries in a CAD model. We can push in, and so we know where every point on the surface is. That allows us to have a ground truth for us to train that network. And then for forces, for the net wrench, you could push into this surface. You have an ATI sensor that's reporting this. So now you have the image of the surface and the net wrench, and you can use that to actually train the network as well. And so this briefly shows ground truth versus estimated forces running in real time, about 20 hertz for these systems. And the gel is extremely soft. Our latest work, TensorTouch, really drives home that final point. We can get all those positions over the full surface. At every pixel, I can tell you what position it is. But now I can give you that 4-axis stress field. Every point, what's the normal, planar shears, and torsion over the whole surface of the sensor. So we had to upgrade our models, and our team grew as well in order to accomplish this. This is the structure and the process. So we go into our FEA solver, finite element method, and we actually apply these indenters to the surface, informed by like the YCB data set so that it's similar to the things you might interact in real life. You then take those deformations, and you then have position and stress field coming from your FEA solver. You might say, why not just use that by itself? Well, the problem is these FEA solvers actually take a few seconds to do these really basic calculations, even if you have really decent compute. And then you can actually take the deformation and then feed it into another tool like Blender, which then says, here's the deformed image that correlates to that deformation. Now I have a data set in Sim between deformed image of the inside of the sensor and the stress field and position of that surface. We then train this model in simulation and then do transfer learning to then transfer it to the real world. And then we have full stress profiles, calibrated stress profiles over the surface of our sensor. So this shows real-time operation. These top 3 rows are from the first sensor, the bottom are from the bottom sensor here. And then I want to kind of show how we're trying to really push towards that string manipulation capability. As a very first step, you'll see my student pinch the fingers, and it's going to hold 2 wires, and he's going to pull on one. The system has to localize both wires, but then pivot to the one that's feeling more force. So you'll see that in a few seconds. So here he's pulling on the cord. It localized both, felt the stresses locally, and pivoted to that one, taking us one step closer to feeling and untying knots. We're not done. These are the things that need to be fixed. Right? We need to improve surface durability. We need to lower the variance in the fabrication method. we like to add additional sensing modalities to really get closer to the human finger, temperature, vibration. And then we need to automate this calibration process so it's easier to make these in bulk, and perhaps have a startup that spins out doing such a thing. And then we want to bring this cost down. Most of that cost right now is in the cost of the camera. This is unnecessary. This is just, the bane of being a researcher who's doing many things. If we found a partner that could bring that cost down, we would do that. The other key is that we use a fisheye lens so that we can use one camera to track that whole surface, and it's using equal angular reprojection. So by having a fisheye lens and a dome, that means that every point on the dome, if you look at the pixel image, is evenly spaced, so nothing is warped. So that's another key factor we need. We need this sort of fisheye lens, single camera system to accomplish this. So what can you do with this? So one of our really early cool works was to say, what if you wanted to reach into a bowl of screws? It's kind of hard to see what's going on, so just figure out where the top mound of screws are. Reach down and then just passively feel what's going on. Find some screws, pivot them in your finger, and then classify what you're holding based on shape alone. So can you actually determine from the head and shaft diameter, maybe even the threads, which screw you're holding? You pinch this, and then maybe your screw isn't perfectly localized, but you know where it is. You can then roll your fingers together using a Jacobian to determine how you can pivot that. And then because we took the time to calibrate, we actually save ourselves on the back end in terms of how much data we needed to train this ResNet to actually classify. We're dealing with low 100 screws, I think less than 200, to actually calibrate this system because we spent all of our heavy-duty energy making this modular component, which is to say we can always give you the raw image if you like, the depth if you like, and then train this downstream head to do whatever you need. So this is the system running at 10x. Grasping this, if you were here at the SRC launch, you would have actually had a chance to actually see this sensor and system running in person with my PhD student who recently graduated, Wang Kim Du. We showed that we could actually quickly transfer this to other items as well. Just switch your data. You can use this for pills and paper clips as well. Now you are fully ready to help grandma sort that bowl finally. Okay. Some other cool applications here is picking really small objects off of flat surfaces. So with that sort of adhesion principle here, you can see us being able to pick up a tiny little nut using electrostatic adhesion. Using the fingernail, we can also pick up things like coins or paper clips, and then you can pick up regular sized objects as well. Some of our more recent work under submission, but on archive, you can check it out, is really thinking about what do we do if we want to handle very soft things. Let's move towards that conversation of forces. This work was being developed in tandem with our TensorTouch, so it didn't fully leverage all of those aspects, but we were able to show that we could still do some really cool things in this space and actually manipulate fruits many, many, many times without damage. Now we're bringing the power of calibration so you could actually transform between different sensing modalities if you wanted to for training in the future. But here you see the raw images of these two fingers. They're deformed image differences. These were trained through imitation learning first, and then we show that we're able to manipulate real strawberries, real tomatoes, real blackberries at scale. If you ask my student Aiden, he doesn't like strawberries anymore. Hope to rehabilitate him in the months to come. Another application here is even detecting small cloth layers. So here in some of our recent work, we're showing the ability to actually say, well, if I have this really tiny silk cloth, can I rub my fingers together? And based on how much force I apply and how they move and what I see, can I actually classify how many layers? And that actually works really well. There might be some instances where you want to combine both vision and touch. So in our work, TouchGS, we used the sense of touch to actually augment vision and actually apply this to those neural representations. So specifically using Gaussian processes, we could then say, well, if I touch a sensor many times, touch an object many times, I can build a point cloud that's high resolution because my sensor is high resolution, and then use this to actually inform and train my Gaussian splat. And so what actually ends up happening is objects that would have been hard to see because they were too dark or reflective or transparent, if I touch it, now I know where that surface is, and then I end up with Gaussian splat representations that are far more accurate. And so here you see ours, there's not as many holes in this bunny, This still looks a little crappy on purpose because we just did a few touches. We could have done many, many more, but we really wanted to drive home how the sense of touch accelerated the accuracy of these systems. Matt Strong here led this work where we said, well, as we're really trying to be efficient, what's the fewest number of touches and perception that you needed? And it turned out that if you use Fisher RF uncertainty, you can actually use uncertainty in your depth representation to determine where you should go next in order to interact with these objects and build quickly these neural representations. So let's go to the other side of this. So when we think about how we actually give these systems intelligence, we mentioned the aspect of using RL simulators because you need an environment you can reset. But these systems really struggle. So Isaac Gym was all the rage not too long ago, Omniverse, but it's depreciated. It was able to do a lot of really cool things with rigid objects really well. Like even the OpenAI sort of orienting the cube in your hand would have been great for this type of resource. But when it comes to the soft things, it struggled, right? It really struggled. So one of the leading sort of simulators in this space is Drake by Russ Tedrick, MIT. And they really started off thinking about robots that have to run and they make contact with the ground. How do you think about those contacts? Because the ground is effectively rigid, but then you have this discontinuity, if you will, in terms of the momentum as it strikes the ground, and these can be hard for differentiable solvers to actually calculate. And so this really led them down the road of thinking about these types of contacts. It's not a solved problem, but it's really, really hard, really expensive. The other side of that coin is imitation learning. How can you learn from human demonstrations? So one really popular method is using VLAs. So there's a lot of hype around VLAs. We're going to bust the bubble a little bit and talk about what some of the challenges are. So we see a lot of companies moving in this direction, but there's sort of three axes of generalization that need to be accommodated: the visual component, semantic, and behavioral. So what you'll look at these papers, you'll find for these different systems, they talk about generalization performance on variations on the task are poor. However, they test on one of the only models from physical intelligence, Pi0 model, and they demonstrated fairly robust task generalization within a particular task, showing that within that same task, completely different and never been seen before environments could do okay. So my student did a few preliminary tests on this. And all of these results that you saw before were within a single task. But a question you might ask is, well, how well can this system generalize to other tasks, across tasks? And this is necessary if you want to have this sort of general AI. And so we fine-tuned on a new embodiment, for instance, and we want to ask, how well could you actually use this to understand these representations? So a few disclaimers for the results I'm just going to show you. The analysis is performed in simulation on a limited number of tasks. They appear in the pre-training mix, and analysis was performed with fine-tuned models. So what we found is of the different task classification types, so this was like the spatial environment, object environment, goal environment, and their Libro environment. If you don't do any generalization, you just train within the set, you get numbers like they provide, like the 96% success. If you withhold some of the data of a particular type of task and then try to train on the remaining tasks within that data set, you still end up with pretty good performance as claimed, 95%. But if you start to do cross-task generalization, going from very similar tasks but across them, maybe training a model on portion of both and trying to do one, it drops considerably. And if you go really out of domain, cross-suite generalization, it's very poor. And so these are some of the training cycles really showing both the performance for the ones that within its own suite, how it would do, and then how these models would perform in these other environments. So a question we should ask ourselves is, if you're going to do this imitation learning, what data is needed? So there's perception, vision, tactile. There's proprioception, how you are moving in the environment. And I'll throw this slide up just to really drive that point home. If you have a calibrated sensor and your person who's giving you those demonstrations has some sort of glove that's giving them sensing, if these modalities are different, having this shared representation of a calibrated position, calibrated force, can really help you in transferring that skill quickly from human to robot. So here's some really cool work from Karen Liu, Feifei Li, called DexCap. And it's really driving home this sort of sensor suite for the person. There's a camera that's looking ahead of the person. They're tracking the person's hands. They're using these Rococo gloves to track the fingers. There's no tactile sensing on the person, but if they're picking up these sort of relatively rigid objects or large objects, they can do quite well. So here's the sensor suite, the RGB camera, the motion capture gloves, and then wrist tracking sensors. They're able to use these to control and collect data for tracking manipulation tasks of the person. And then they've used this with the LEAP hands on bimanual systems to actually perform that manipulation. But I want to drive this really quick, interesting point home, which is the challenge of retargeting. So if you go into their paper, you'll see this image, and they're using an off-the-shelf Pi bullet to actually perform the IK between the person's finger and this finger. If you've ever used an IK solver and move it and you could take your time, you could describe a pose you want, and then the robot's able to figure out how to move to that position, and it's able to do it. But if I'm doing real-time tracking of an arm, you may not have a lot of computation time. And so what you end up using is differentiation. So if you actually go into this library, into the documentation, they'll tell you, well, actually, under the hood, if you're doing this in real time, you're using damped least squares. So what's happening there is if I have forward kinematics, which say if I have these joint angles, where's my hand? And I differentiate that, so I have the relationship between joint velocities and task space velocities. That's your Jacobian, which is a function of the angle of your system. And a challenge here is if you go to extreme poses, like fully extend your hand out, that is a singular pose, which means every motion in your task space does not uniquely map to motions in your joint space. If I'm fully extended and I go extend further, how do I do that? I can't, right? Here, I can go in and out, up and down, left and right. That's a high rank pose. This is not. So this becomes really a problem when you think about embodiment. You have the human hand size, leap, shadow, move, leap. All of these are very different in their form factor, number of fingers, size, scale. So it's not reasonable to assume you can just always track the angles of the fingertip. You really probably want to think in terms of the task, which is going on at the fingertips themselves. So this leads to the last piece I'll discuss and then wrap up here, which is a tool we call JParse, the author of which just defended and is sitting in the back. If tasks are hand or fingertip centric, how do we handle differences in link lengths for task descriptions? We as humans are able to do this very naturally. If you think about a baseball player or any sport, they can move really quickly, throw their arm out, catch a flying ball with no problem, no considerations for the singular poses they might find themselves in. How are they doing that? They have some desired pose they're trying to track. They're paying attention to their hand, but they don't seem to be paying a whole lot of attention to how every single elbow, every single joint is moving in order to achieve that task, right? So this is the objective function, if you want to think of it in terms of controls that they need to minimize. And then we talked about those forward kinematics that map the joint angles of the person or manipulator, arm or kinematic chain to the end effector position. Here we'll focus on just a 2D example. 3 links, 3 angles, some XY position of the end effector. If I differentiate this, this tells me how my end effector will move, its velocity, as it relates to how my joints would move at this particular pose. And this is a high rank pose, which means if I take this Jacobian and I actually look at the pseudo-inverse, this component here represents, its main axis represent the manipulation ellipsoid. So a singularity, as we were discussing, is kind of as you extend your arm out, that ellipsoid becomes highly eccentric. And when you fully stretch out, this domain really flattens out and becomes 0. You lose that dimension. And then if you try to invert, if you think of the ellipsoid as your determinant and you try to invert that, it's 0, and now you have division by 0, and bad things happen. Trust me, very bad things happen. So we want to avoid that scenario. So our approach was to say, let's solve this in a few steps. If I ever start to move into a pose where I'm getting too eccentric on one axis, I'm going to define a new Jacobian called the safety Jacobian, which is not allowed to shrink more than a particular aspect ratio. Even though the true Jacobian is shrinking, I'm going to mathematically store this Jacobian for future use. Second, what this does for me is it prevents the collapse of those manipulation ellipsoids along those singular directions. And then my goal is to also preserve the dimension of the ellipsoid along the non-singular directions. So to accomplish this objective, this is not the only thing I need to do. This is very similar, if I only do this, to the damped least squares, which you saw actually in the previous slide. for how the pi bullet IK solver worked. But what I can also do is I can say, well, if you're asking me to do something, you're asking me to move in a particular way, can I take that commanded vector and project it into its components that are along the axes that are non-singular and let those be retained as they are, then project them onto the axes that are singular and scale them by a scale factor. And that scale factor should be related in its numerator to that singular value. So if you're getting really, really, really close to your singular outstretched position and you actually reach it to some large number of decimal points, you can't move, right? You're fully extended, and that makes sense. That's just physics. But if there's a little bit of play, and for most arms, if you actually look at the floating point numbers, like 16-digit floats, you almost never get your arm out to all 16 digits. If it does, it doesn't stay there very long if you don't have a lot of friction. Then if there's just a little bit, then that means there's a little bit of volume, and that means this number is going to be really small but present. And if it's small but present, and I take a projection onto it, it might take a while, but I can actually pull myself out. So this algorithm, if you read the paper, we show asymptotic stability. If you start anywhere, you can go to any point with asymptotic stability of ignoring self-collisions, but including a singular pose. But if you're truly in a singular pose, you have to stay there. But if you're just a little bit out of it, you can actually get asymptotic stability to any point again. So this drives those point homes, those two components for the forces, and I'll keep moving us forward in the interest of time, but this is what the completed network looks like. I have some commanded vector. I project this through. I can put some gains on it through the singular directions, the non-singular directions, multiply it by the safety Jacobian pseudo-inverse, and now I have this new commanded joint velocity that allows me to accomplish this goal. And this is very useful for velocity control. Another objective you might have is, well, what do I do with my null space? So if you don't, your arm might kind of fall in the dimensions that don't matter to your task space objective if you have a redundant robot. So just attracting it to a nominal pose is a good idea. And this was our method of using that safety Jacobian to achieve this. Spoiler alert, there's actually a torque version of this which will come out soon, so keep your eyes peeled for that. So this is the paper kind of overview of the whole system that I just mentioned. You have this J, decide if you need to turn it into a safety Jacobian, break your commanded vector into feasible directions, singular directions, scale the singular directions as needed, put this together in a modified command, put it together for the joint velocities. So quickly showing you and wrapping up the sort of performance of these systems. This is damp least squares, which was the pi bullet example. Notice how these arrows aren't really on top of each other. Now you might say, well, could I tune some gains? Absolutely. But if you tune those gains and make them too small, then when you actually stretch out here, it'll behave more like the regular Jacobian pseudo-inverse and dance around and go crazy. And I'll show you what that looks like, I think, in a second here as well. J-parse, on the other hand, you show high accuracy, asymptotic stability to points that are within reach. And then when a point goes out of reach, you're able to do that as well. So here shown, the red is the safety Jacobian in just the position space. And then blue is the true Jacobian there. So I'm going to speed this up, this example here. And I promise I'm almost done. So here we are dealing with a just off-the-shelf, really cool arm, X-arm. We're asking it to reach out and grab this cut that's at the boundary of its workspace. Boom, you see that stop? That's because their safety mechanism said, you're approaching a singularity, you're going to crash this robot, and it stopped us. But if you use our method, you can still control that task space, reach all the way out, grab this object successfully. And then I'm already fully extended out, but all I have to do is just pull back the lever and wait. And then it's able to come out of that singular pose. So this has been a problem for decades, and I'm very proud to show that we've been able to do this. And it's already starting to help a few startups, we've been told, and even other labs that are doing work in controlling like wheelchair-mounted arms. Other really cool examples, I encourage you to check out the website. Go to our lab page, arm.stanford.edu. I think there was a QR code a moment ago, not this one, that you could actually check out. And on that one, you could actually play a video game on our website that shows how this works. So it's really fun. Check that out. So key takeaways, and we'll wrap up. We'll stop here. Reliable manipulation is key to the next generation of embodied intelligence. The best hardware, I believe, will lead to the best data. And humans are really good at most things we want robots to do. So it would be wise for us to extract demos in a manner that is natural for the humans to perform for us. With that, I'd like to thank you for listening and answer any questions.
For the tactile sensors, though, I was wondering, like, how would you make it smaller? Like, if I want to manipulate smaller objects or create a bunch of them on a robotic hand, like, what needs to change on the hardware and in the software to make them smaller?
So the question was, how do I make perhaps the optical tactile sensors smaller? But baked in that, I think, was a second implicit question, which was, maybe I don't want it just on the fingertips. What if I want this sensor all over the body? So I'll answer those two pieces. For the shrinking aspect, the main challenge is really the camera, right? LEDs are easy to kind of make smaller. We can get really small ones like that. The camera is the challenge, and getting a camera that has a fisheye lens and has an optical focal length that's really small is the key. We don't think that that's particularly hard to do. You just have to find someone who knows how to model the lens correctly to get you there. My dream in the next few years would be able to get a version that could fit inside the human thumb. I imagine you could even get smaller. And if you actually check out some of the work from my colleague Mark Kukolsky and one of his PhD students, I think it was Julia D., they actually did a version that actually used a camera and optical fibers to actually send a smaller image to a smaller area, and they're looking at how to use this even in probing activities as well. The second part of your question, which is coverage over the whole space of the finger, that might not be computationally tractable, right? If I have, one camera even for the whole fingertip, then how many do I need for my whole hand? I might be at 20, 100 cameras if I want to fill the whole hand, and if I want it over the rest of the body, where do I put all these cameras? That might not be the most tractable method. So I think something you could probably take a playbook out is, again, being biologically inspired. We don't actually have the same density of sensors over our entire body. Our face, our hands, our feet are super dense in terms of the tactile sensing resolution. Other places are less. So maybe you can use other sensing modalities on other areas and places where you think it matters most to have megapixel resolution, put those sensors there. And I think there's some really cool emerging techniques, even in the physical transduction space, that might lead to, in the very near future, really nice tactile skin that, again, can give you those 4-axis sensing normal planar shears and torsion. Great question. Yeah.
Quickly jumping off of that question, like in one of the videos you showed
How, for the optical tactile sensing, it was able to pick up very small screws. Like, how were you able to make it pick exactly one screw out of a ball of a small screw?
Yeah, that's a fantastic question. So the question was, in the interfinger paper, when we're reaching into the screws, if you grab multiple screws, how are you able to actually localize just one or a few? So to do that, when we would grasp, because our silicone is so soft, I want to say it was a shore hardness around 10. Again, just check our paper. But as you go and you reach it, you can grab a bunch. Sometimes we were lucky, we would grab one, then you're done. If you grab more than one or a few, then the question would be, how close were those screws? So if they were far enough away so that I could roll my fingers over a particular screw with enough gentle of force that my contact area only contains the screw of interest, then I can roll my fingers together, center them on the screw I want, loosen the grip a little bit, and then I can drop the ones I don't want. And so that was our technique to kind of address that, that ability. I think in the paper, we showed that we're able to actually do that. We could roll our fingers to drop a few. But I think we kind of were more on the side because it didn't happen so much for the screw sizes we were dealing with. If we picked up two, we might drop them and try again many times they were. So. Yeah.
I was curious kind of on the other side of that with respect to the kind of deformability and softness of the surface that's being used for the sensor. If there's any classes of objects where that material struggles with the more dexterous motions.
Yeah. It's a great question. So the question is there a disadvantage to being too soft in sort of manipulation tasks? That's a great question. I would say there's one inherent challenge, which is hysteresis of your sensor. So if I'm so soft that given the strength of my material, I kind of deform under my own weight, that's not good at all, right? You kind of want, under your own weight, you should be able to actually retain a particular pose and stiffness, low hysteresis. That would be ideal. But for interacting with the world, I think the question is perhaps, are there instances when you actually need more force to accomplish certain tasks? So I believe it's Professor Hannah Stewart at Berkeley. She's developing optical tactile sensors, but she's making her sensors very, very strong so that she can handle much harder things. And I believe she's using polyurethane to actually really be able to handle tough things. So it's really application dependent. If your sensor were robust and extremely soft, I don't really see a big disadvantage, and I would probably use our fingers as kind of a stand-in for that, right? We have very soft fingers, and yet we do many things. Probably, though, if you're doing rough things, we build calluses on our hands or we use gloves. So any task that would cause abrasion and tear the material would be a consideration for that. Other questions?
Yeah. The main question is, I see a lot of robot hands coming out every couple of weeks. There is almost a release at this point, and a lot of them really try to mimic the human hand very closely. And I'm very curious what your thoughts are about to what extent dexterous robots actually need hands that look like humans, or can they look different? And this week there was a release from a startup called Sunday Robots. Their answer was like 3 fingers is all you need, right? So I'm very curious about that, and if that also affects the design of the tactile sense.
Yeah. That's a great question. So just repeating it, are human morphologies necessary for hands? There seems to be a trend in fabrication to do that, with a few outliers, maybe biased towards 3 fingers. Is that necessary? Great question. I think there's a few ways to ask or think about that, considerations. One would be from the perspective of actually achieving a stable grasp, and I'll put on my very formal hat going back to the form and force closure, right? There's a lot of things I can't do with 1 finger. I can do more things, but there's a lot of things I can't do with just 2 fingers either. If I want to do finger gating, I need 3. And maybe finger gating might be a little bit easier if I had 4, right? So form closure, finger gating might kind of drive some of these kind of considerations for how many contact points you want. But then again, if I'm really strictly in that sort of mathematical space, who says that the abduction range, for instance, needs to match the human abduction range or form factor? It's not a necessity at all from that perspective. Another angle you might approach that question is the imitation learning perspective. So if a human is teaching me and a human has a particular embodiment, if I want to learn faster, maybe matching my morphology to the humans might accelerate some of those capabilities. Another is the task-driven aspect. So if you kind of talk to customers who might want to use these hands, I had a chance to talk to like a semiconducting company a while ago. There are machines that take months to build, and the technicians have to reach their hands into tiny little spaces to screw and handle all of these things. So if your hand is much bigger than that, maybe you can't necessarily go where a human can go. So at a high level, I would say the beauty of robotics is the diversity of solutions you can apply. I don't think there is a strict requirement that you have to have an anthropomorphic form, but perhaps if you want to learn from humans faster, it might be easier to do that. But at the same standpoint, my student who just left, she's asking a similar question saying, well, if you have tools like JParse, right, and you only care about what's happening with the fingers, maybe that's where you focus your energy. Maybe it's less important that your embodiment be the same, and really you match the contact points which are necessary for the task demonstration. So I think that's a huge design space, and I think those are probably the main considerations for them. And then of course, from perception, I think this is a question that our lab and a few other labs are partnering together to say, well, actually we should do an ablation. We should really prove and drive home what do you actually need to be successful in manipulation. And right now it's the Wild West. Everyone is making their own tactile sensor. Everyone's making their own hands. How do we judge? Everyone's getting tons of funding or not, right? How do we know who's better or not? Well, if we're done playing games, I think what we should do is come in and have humans collect a data set for us, right? Have a human walk in a human-based environment, a home environment, agriculture, industrial solution, have them collect this data, and that'll do 2 things. If we fully outfit this person, see what they see how they move, see what they feel, right? We can take that information, and A, that's useful for training robots, but B, it establishes a benchmark. If I say, I want you to pick 100 strawberries with the quality of a human being, then I need and human beings to statistically show me what successful strawberry picking looks like today, and that's your number to beat, right? And when you do that, tie your shoes, pick the strawberries, assemble the phone, do all the home chores, both rigid and soft objects. There are going to be a ton of tasks that are just immediately out of our reach, like tying the shoes. But that's okay. If we don't set the bar, we'll never know when we pass it. So I think that's what needs to happen next. Yeah.
You mentioned the iPhone construction case as a sort of case study. It seems to me there's some amount of feedback between the process, the way iPhones are designed, so that they're actually difficult to assemble. In other words, it takes a person to assemble them. And I suppose some of that is maybe an actual constraint for the size of the iPhone, but maybe also it's intentionally kind of misdesigned so that it's hard to construct, and therefore hard to deconstruct, perhaps. So I wonder, there's got to be some feedback between the design of the industrial process and the whole thing and what you're designing for.
Just to restate that question and point, and make a comment to that point, which is, as we think about particularly the industrial scenarios, maybe the devices could be designed in a way that make them easier to construct, and maybe that's actually a design component right now for these systems, the difficulty to design them so that perhaps they're harder to reverse engineer at the moment. So I would say, these are real problems, and I think two things kind of come out there. One is designing your world to be easier for your robot. I think a question to ask there is, how easy does it need to be? Maybe there's too easy, but maybe it can be easier to construct, right? Legos are Legos for a reason, because they're easy for kids to manufacture, put together. Modularizing your systems, making them easier to handle might be an advantage. But I think another piece that's there is the IP protection component. If you want to protect your IP, and you require a larger team, an international team to construct it, right? How do you protect that IP? So I think actually having robots that have advanced manipulation capabilities allow you to potentially onshore your construction. And now, it can be easier to make because you don't have to make it everywhere. You can make it wherever you want to deploy it. So I think having these systems can actually address that side of the problem as well.
I know that you mentioned a lot about rigid and soft objects, and I was wondering if you ever considered like texture identification. I know that for us, a lot of it is based off of the texture of an object and how we would manipulate that object.
It's a great question. So the question was in that manipulation space, what role might texture play in understanding how you might manipulate and interact with an object? A lot of my colleagues in the space of haptics, so haptics is displaying tactile sensations on a person so they can perform a task, have asked some very similar questions in those spaces, and it's been really challenging in the haptic space to replicate real-world sensations like sandpaper or the others, but they have some decent approximations and even some new tools that have recently come out as well. But I think the short answer is yes, right? And particularly, I'll go back to the vibration question, right? If I'm running my finger over a smooth surface or a rough surface, how my mechanoreceptors respond to those materials is an artifact of vibrations and that interaction. And that might influence, for instance, a task you're trying to do. Maybe a rougher surface is better for friction, for instance, to where you might choose to grasp something. So short answer is yes, I think it will inform and is useful to know. The how, I think, can come in many different forms, perhaps like in the optical tactile sensing space. If I have high enough camera resolution and soft enough gel, I might be able to actually see that pattern on the surface of what I'm touching, if that's visible. Or if I have some manner to extract vibration as well, that could also be visible there as well. So short answer is yes, and I think there are paths forward to deploy that on the sensors. Yeah.
Example, if there exists of like an adversarial image or stimuli, but for touch, and you know how that would look like, in which you would optimize the sensor in a way so that it thinks it's something, like it's feeling something, but it's really not there. Like, how would that look like?
So the question was, how might your system deal with potentially adversarial contexts and sensations? I think. Realistically speaking, you may not experience that from external objects as much as you'd expect, but I have seen some recent work, emerging work, that have really talked about maybe how might you know when you're making self-contact, right? So if I'm holding an item between my hand, maybe part of my hand is holding the actual item, but maybe part of my finger is touching myself. How do I identify that so that I don't make decisions based on self-touch versus object touch? And that's an active area of research. And again, machine learning is proving to be very useful for those types of questions. Fantastic. Well, thank you very much for having me. Emails.